Hi there. So this is going to be the last of the equilibrium videos, at least for new instructional material. We're looking at content from Chapter 15 of the Adam's First OpenStax chemistry book, second edition. I've also pulled some examples here from a PowerPoint that went with the Coates textbook, which I think is a good set of examples. So we're not going to cover the whole chapter. Mainly we're going to deal with the precipitation and dissolution and coupled equilibria. Lewis acids and bases we talked about in chapter 14 to an extent. We're not going to talk about equilibria stuff related to them in this video. So here is fluorite, which is a precipitation of a mineral that's created deposited through a precipitation process. What we're dealing with here is looking at precipitation, looking at it in a little more complicated way than we looked at it in the first sturgeonal chemistry, when we basically said things were soluble or they weren't soluble. There was a little asterisk there that said that some limit like 0.1 molar solutions at 25 degrees C or something like that. We're going to look at precipitation and dissolution type reactions, which of course are the opposite of the same reaction, and look at it a little more quantitatively and with a little more subtle view to it. This is common, usually you'll hear in the intro course, one story, and then in the next course you'll hear something, the story's a little more complicated, and as you go up, you become more aware of the nuance and more aware of the existing uncertainties, the questions that are left to be answered. So there are going to be a set of computations that you deal with this, so they're basically the same equilibrium concepts applied here. They look a little different, just because it's a precipitation or solubility equilibrium. So this slide makes reference to that earlier slide. I think this is supposed to be don't here. I think that's a typo. They don't dissociate in the compounds. So the truth is they do dissolve to a small extent. They're sparingly soluble, and it's an equilibrium, and this is an example of a solubility equilibrium where you have a solid and an equilibrium set up to the dissolved ions, and obviously the solid is the more common form for things that we say are insoluble, which is why they say that the K for this is much, much less than 1. From the Coates presentation, I pulled up some values of this K. This is called KSP for K solubility product, and you see some values for each of these different minerals or these insoluble compounds. Some applications for them or common names for them there, and then you see those values, which are typically much less than 1. So here's a picture of what happens if we put our solid silver chloride here. So the green, I imagine, is the silver ion, right? And the gray is the chloride ion. So that's solid silver chloride, and you see that would represent a silver +1 ion. That represents a chloride ion. So a few of them still do dissolve, but again, not all of them for the most part. So we take these sorts of equilibrium and we write the equilibrium expression. So if you're writing the equilibrium expression for this particular equilibrium, it's going to be K, and K would be the product, so strontium 2+ concentration times chromate ion concentration. And then you think about putting the reactants on the bottom, but you notice the reactant is a solid, so we leave it out of the equilibrium expression. All right, sorry for the screen disruption there. We'll leave that out of the equilibrium expression, the K expression, if you will. So it's going to just look like that. That is two things multiplied together. That's called a product. So this is called SP for solubility product, KSP. And here you see the value given at 25 degrees C for the strontium chromate compound. So it's not very soluble. Now, so what would you do experimentally to do this? Well, you're going to add the solid that's not very soluble to water. Eventually the solution becomes saturated with ions, reaches its solubility. If you have some way of measuring those ions, you could then calculate the solubility from its KSP value, and we can convert that to something called the molar solubility, which is the moles per liter that are soluble. So here's an example I pulled from the Coates book, which is a good example for this. So the KSP for magnesium fluoride is 5.2 times 10 to the negative 11th. And we're asked to calculate that solubility in both moles per liter or molarity and in grams per liter, which might be the more common or more practical concern. Of course, the equilibrium here is MgF2 solid in equilibrium with magnesium 2 plus ion plus 2 fluoride ions that are dissolved in solution that are aqueous. Usually if we have charges there, we don't have to write AQ. It's kind of implied, but we can write that. So when we write the KSP expression, you see you have magnesium concentration times the fluoride concentration squared, where that 2 and that 2 are the same. That's where that subscript 2. So we can make a ICE chart here. They call it a RICE chart, reaction being the R for rice table. We leave the solid out. We start off with 0 magnesium, 0 fluoride. If the magnesium increases by X, the fluoride increases by 2X. And so at equilibrium we have X molar magnesium 2 plus and 2X molar fluoride. We're going to plug that into the KSP expression. So that KSP, this becomes X, and that becomes 2X from the ICE chart. 2X squared is 4X squared, and then you multiply that by X, you get 4X cubed. And the solution for that will be the cube root of the KSP value divided by 4. And the KSP we told before is 5.2 times 10 to the negative 11th. So divide that by 4, take the square root, and we get 2.4 times 10 to the negative 4th, which is the molar solubility of the magnesium fluoride. To get the gram per liter solubility, we're simply going to take that molar solubility here written, this is our molar solubility, that we got up there, written that way as a fraction, and then simply convert moles to grams using the molar mass here, and we get the value of 0.015 grams magnesium fluoride per liter that are going to dissolve. The other way we can do this is we can calculate the KSP if we have some way of measuring the concentration of the dissolved ions. And so if we're given something, or we might be given either molar solubility or the gram solubility, we have to convert it into the molar solubility to do that. Here's another example. So we discover that the solubility of lead-2 iodide is found to be 0.00130 molar. Can we calculate the KSP for lead iodide? Well, lead iodide dissociates, as you see here, PbI2 solid in equilibrium with lead 2 plus ion plus 2 iodide ions. We write the KSP expression, and then we think about our ICE chart. So in our ICE chart, which they left out here, so let's write one. So we got, well, I'll put it down here. So ICE. Leaving the solid out, if we start out with 0 of this and 0 of that, this is going to be plus x. This is going to be plus 2x. So x and 2x, just like the example before. The amount of PBI2, if we'd started out with this and put a change here, we would have put minus x. That x is the molar solubility. So from that we figure out that this must be 0.0013 for this one, so that shows up there, and that this must be 2 times that, or 0.0026, which shows up right here. Okay, so there's an ice chart behind this thinking. Now we simply plug those into the KSP expression. So you see those two values again from the ice chart here. This was our x and this was our 2x. And we remember, of course, to square this. And we come out with the value of 8.79 times 10 to the negative 9th. The 4 here is the 2 squared, so that's 2 squared. And then what they're saying is that 0.0013 times 0.0013 squared is 0.0013 to the cubed. That's the way they've written that. But if you plug this expression right here, this one, into your calculator, you should get 8.79 times 10 to the negative 9th. And again, I can't stress enough practicing these calculations so that you do know how to enter these problems in your calculator. Now, the common ion effect is a term for what we really have been talking about with buffers. We talk about a buffer having a conjugate acid and base pair, both members being present. If we're thinking of the acid, then the conjugate base is what we call a common ion in the equilibrium. And so in this case, we're introducing that common ion through a much more soluble compound that contains the ion. So looking at barium sulfate here, barium sulfate is slightly soluble. The solubility equilibrium is written up here where we have a equilibrium sign and then barium plus sulfate. The sodium sulfate is a one-way equilibrium. It's going to give me 2 sodiums because there's a 2 there, plus sulfate ion. And what's going to happen is that sulfate ion, since it is a common ion with the barium sulfate equilibrium, that's going to increase the concentration of the barium sulfate. So if we were writing an ice chart for the barium sulfate equilibrium, and this is solid, so we don't really care about that. We have 0 barium ion initially, but what we're going to have is 0.10 molar sulfate ion from the sodium sulfate. So when we say plus x in the second line, and we have x and 0.10 plus x, if we plug that into the KSP expression for barium sulfate, that's going to be barium concentration times sulfate concentration. If no sulfate ion added, then it's going to be x times x. If 0.10 molar sulfate added as the question here, then it's x times 0.10 plus x. Both of those have to be equal to the KSP value. The plus 0.10 is going to make this term at the bottom bigger, right, than the version there, which means that this term is going to have to be smaller. So we're going to have less of the barium sulfate dissolve in the case where the common ion is present. And this repeats the question there. And we could go calculate that. It'd be a bit of a problem. Let me pause here for a second and make sure I got the barium sulfate value, and I'll show. All right, so I looked up on slide 6. The KSP for barium sulfate is 1.1 times 10 to the negative 10. So if we have no added sulfate, as we said before, that's going to be 1.1 times 10 to the negative 10 is going to be equal to X for barium times X for sulfate, the example that I gave without that. So X squared is 1.1 times 10 to the negative 10, and X is then going to be the square root of that, so that's going to be something around 10 to the negative 5th. Yeah, 1.05 times 10 to the negative 5th, and that's the molar solubility with no added sulfate. So if we have the added sulfate, we have 1.1 times 10 to the negative 10 is now equal to X times 0.1 plus X. That's 1.1 times 10 to the negative 10 is equal to 0.1x plus x squared. That's a quadratic. We might assume x is very small. That's probably acceptable. So if we assumed x was very small, we could say x times 0.1. So that would make this much simpler. It's just going to be 0.1x. It would eliminate the x squared term. So the approximate solution is going to be 1.1 times 10 to the negative 10 divided by 0.1. That's, I think, going to be 10 to the negative 9th. Yeah, 1.1 times 10 to the negative 9th. If we took this equation as we had it and we throw that into some more rigorous analysis program, like for example Wolfram Alpha, we can test this one. I have Wolfram Alpha on my phone. It's something I find myself using a lot. I've given you a link to the Wolfram Alpha website before, so I can type this equation in. 1.1 e negative 10 equal to parentheses x parentheses 0.1 plus x. And one nice thing Wolfram does is it gives me back its interpretation of what I wrote. And let's see if it agrees with me. Yeah, it does. And we get, as usual, you get two values, and the positive value from Wolfram Alpha. Just checking out our approximation wasn't good. 1.1 times 10 to the negative 9. So the approximation solution is good that we did that. So again, that's something that in some situations, traditional exams, you're not going to be able to access something like Wolfram Alpha, but it sure is nice to have. But it's good to know these approximation skills to solve this equilibrium. So anyway, so what we see is that from 1.05 times 10 to the negative 5th, it goes down to 1.1 times 10 to the negative 9th. That's a 10 to the negative 4th change. So it is 1/10,000th what it was before. That's a pretty big change due to that common ion. Here is an image of an X-ray where you have barium sulfate being used as a contrast agent so that you can visualize the GI tract. and this is commonly called a barium swallow. And barium sulfate is used. Barium is not a good thing to have in your system generally, but the nice thing about barium sulfate is not very much barium ion is there, right? 1.05 times 10 to the negative fifth in our calculation with no added sulfate. So barium sulfate just passes right on through the system without getting into the bloodstream and doing bad heavy metal type stuff. If they gave you barium nitrate, it'd be a very different result because that's very soluble. So anyway, so you can look at this from the other direction, and there's a great lab in our second GChem lab that we sort of use as a final project, where you're asked to do some experiments to try and determine what KSP is, mixing together the solutions where you're adding the ions to water. So you might add something like, if you were adding strontium nitrate, okay, which is going to give you, strontium 2+ ion plus 2 nitrate ions, and then maybe sodium chromate, which again is going to give you 2 sodium ions plus a chromate ion. And those two can then mix, SR2 plus CR4 2-. That will possibly form the strontium chromate precipitate if the concentrations are high enough. And here's an example of those solutions. They use potassium there instead. What you're doing then is you're calculating, how much you're mixing, right? So if you were mixing 0.10 molar strontium nitrate, and you were using 1 milliliter of that, and you were adding to that 1/10 of a milliliter of 0.01 molar potassium chromate, you can figure out what the volume of the ions would be. You could use M1V1 equals M2V2 and get the concentration of strontium ion. So strontium is going to be 1 milliliter times 0.10 molar divided by the final volume, 1.1 milliliter. So let's see, that's going to be basically 0.1, a little smaller, 0.0909, say 0.091 molar, and your chromate is going to be 0.1 milliliter times 0.01 molar over 1.1 milliliter. That's going to be a lot smaller. 0.1 times 0.01 divided by 1.1, 0.00091 molar. So your Q, okay, which is your reaction quotient at any time. Sometimes in KSP that's called P, because it's P is for product, Q is for quotient. But Q for this situation then is going to be 0.091, the strontium value, by times 0.00091, the chromate value. So I get a Q there of 8.3 times 10 to the negative fifth. Then you could look at whether or not precipitation occurred. So if you have a precipitate, that tells you that Q is greater than KSP, which means that the KSP has got to be less than 8.3 times 10 to the negative fifth. If you had no precipitate, then that tells you that Q is less than KSP, and the KSP would have to be higher than 8.3 times 10 to the negative fifth. The nice thing about the lab that we do is that you then have to kind of make decisions on the fly about what solutions you're going to mix to try and narrow down the value of KSP by arriving at numbers that you know either are above and below it. And what you want to do, obviously, is get the highest number you can that you know it's above, and the lowest number you can that you know it's below, and then the KSP is in the middle, and you have a tight region of uncertainty. So here's that description of the magnitude of Q versus KSP there. We can also apply this to separations of different cations, and you can use this to purify substances. You can use it as what's called a qual scheme, QAL scheme, which is a scheme for qualitative analysis of ions, where you use these different reagents that provide usually the anion that precipitates things out. So, you might start with a mixture of ions, and the first thing you might do is you might add, 0.1 molar sodium chloride, and what will happen is that the precipitates, well, the chlorides that are insoluble are silver chloride, could be mercury 1 chloride, and I think lead 2 chloride, right? And all the other ions would still stay in solution. And then you can do other tests which continue to split them out into the insoluble or precipitates and the soluble ones. And that's the basis of the qualitative analysis scheme. So they talk here about using carbonate ion to separate magnesium ions from sodium ions. And you see here, then if you're looking at magnesium and barium ions, the KSPs are, only different by a factor of 10,000. So you have to be pretty careful there about adding your source of carbonate ions, which are probably sodium carbonate that you're adding. You're asked which carbonate complex will precipitate first. Well, you can't just compare the KSP values because you have to think about stoichiometry, which means the ratio of the cation to anion. But basically what you're going to do, if you're trying to figure out which one's going to precipitate first, and assuming the concentrations of those ions are the same, basically we're going to write your KSP value here is barium 2 plus times carbonate 2 minus. So if we solve for carbonate in this case, we're going to get the 1.6 times 10 to the negative 9th. That's the KSP for the barium over the barium ion. If we're looking at the magnesium case, solve again for carbonate. That's going to be 1 times 10 to the negative 5th over the magnesium ion. And so if those two concentrations, the barium and the magnesium, are the same, simplest case, if they were both 1 molar, then obviously the magnesium is going to precipitate out first at a lower value. If we calculated the value, this would be the maximum. This value here and here would be the maximum carbonate before precipitation. And whichever one has the lowest number, which will be the one for magnesium, would tell us which one will precipitate first. But if you're looking at compounds that have different ratios, right, then you have to do a more complex. So if I was looking at, instead of barium and magnesium carbonate, if I was looking at something like aluminum carbonate, where I have 2 aluminums and 3 carbonates, that KSP is a lot more complicated. It's Al3 plus squared CO3 minus 32 minus cubed. So the concentration of carbonate would be the cube root of the KSP value divided by the aluminum concentration squared. So while making the comparison between barium and magnesium carbonate is pretty straightforward, if you put it in something like aluminum carbonate, that's going to be a much more complicated kind of comparison, and you have to actually know some numbers to get that done. So that's that. A lot of times, if you've ever had blood samples taken, anticoagulants will be added to basically tie up the calcium ions to prevent the clotting process to happen. If you look at the biochemical process that gives rise to clotting, a lot of biochemical processes involve those divalent cations like calcium ion have to be involved in them. So that's an example there of that. Here's another case. This is a wastewater treatment facility, and they frequently pre-treat the wastewater before we release it back into a river or something, and precipitations are used in that process. Here is an example of a KSP citing example in the book where you have cadmium ion present, and you're going to see a common ion effect. So this is a common ion problem where you've got the cadmium ion existing. So that's example 1513 in your textbook there. Frequently we can dissolve up some precipitates if something has an anion of a hydroxide or say a carbonate or ammonia's present. Those will react with acids and dissolve. In some cases, we can use Lewis base, and we're not gonna deal with that much again. But sometimes we can form a complex ion. So there's ways that we can dissolve precipitates using these KSP ideas. So again, things that have hydroxide, things that have ammonia, or any other kind of weak base can be dissolved up with strong acid. And so if you do that, you're in essence linking two equilibria here. The zinc hydroxide KSP, right, is that K. This is 1 over KW for that equilibrium. So the K for this will be equal to the KSP for zinc hydroxide, which presumably is a small number, times 1 over KW, which is going to be a large number because KW is a small number, right? Well, KW, remember, is 1 times 10 to the negative 14th. So that 1 over KW term is going to be 1 times 10 to the positive 14th. And so that's going to make this product equilibria be much bigger and happen much more reasonably. And that makes sense from chemical point of view as well, that the hydrogen ion is reacting with the basic anion there and forming water. So again, we're thinking about Le Chatelier's principle there. So that's another thing. So we're not going to talk about the complex formation, so we're going to skip this one for this class, so you don't have to worry about that. Okay, so that's the last little bit on the KSPs. I will be posting some quiz key videos later on. Be sure to take those quizzes online, and test is coming up.